Hi everyone. Today we're going to be starting Chapter 10. Chapter 10 is all about sequences and series. In this first section, we're just going to look at some definitions and notations, some different ways we describe sequences and series, and some of the different ways we have to compute the value for specific parts of a sequence or series. So we're going to start in the first half of this lecture talking about sequences. So we define a sequence as a function whose domain is a set of consecutive integers. So for example, the domain could be 1, 2, 3, 4. It could be 7, 8, 9, 10. It could be 2, 3, 4, 5, 6, 7, 8, and continue on forever. All of those are okay. What you can't have is something where you skip an integer. So 2, 4, 5, 6, 7, 8 would not be okay because you've skipped the number 3. Just as a convention, if the domain is not specified, then we just assume that the domain starts with 1. That's what I mean. So for example, the domain for a sequence is going to look like 1, 2, 3, 4 all the way out to some number n, depending on however many terms we have in the sequence. And the range is going to be these specific values. So the names we give these values are a1, a2, a3, a4, an, where this subscript here is like an index, so it describes the order in which this term appears in our sequence. So the first term, we give the subscript a1 because its domain that it pairs with is the number 1 because it's the first value. The second value in our sequence we use the symbol a2 to describe because it's the second in our sequence, and so on all the way out to an. So the domains we typically call the term number. It describes the position of the term in that sequence. And the ranges are the actual terms of the sequence, or the term values. So we'd say the first term, the second term, the third term, the fourth term, and all the way out to, say, the nth term. So we have two types of sequences that we can classify by their number of terms. We have finite sequences. A finite sequence has a limited number of terms. So for example, if we have the sequence 2, 4, 6, 8, this sequence has exactly 4 terms. The first term is 2, so a1 would be 2 because its term number is 1. It's the first number that appears in that sequence. The second term is 4, so the a2 would be 4 because it's the second term in the sequence, and so on and so forth. But we have exactly 4. There's a limited number of terms, so this is considered a finite sequence. An infinite sequence continues without stopping. So for example, if we have the sequence 2, 4, 6, 8, and then we have these ellipses at the end, that's what we call the name for these 3 dots. That means that this sequence is going to continue forever, following the same pattern that we see going on here. So sequences, it's going to be often valuable to us to be able to describe them using a rule or equation. So for example, if we take the sequence 2, 4, 6, 8, and really it doesn't matter if it's finite or infinite, you'll describe the rule describing them would kind of be the same. So this one, we would say, the rule is a sub n is equal to 2n, or you could write it as a function notation, f of n is equal to 2n. Well, why does that work? Well, if I plug 1 in for n, we'd have a sub 1 is equal to 2 times 1, or 2. And we see that, yes, indeed, the first term in my sequence is 2. If I put 2 in for n, we'd have a sub 2 is equal to 2 times 2, or 4. And we see indeed the 4 is the second term of our sequence. If I put 3 in for n, we have 2 times 3, which is 6. And we do indeed see the third term in our sequence is 6. So you guys hopefully get the idea there, right? So we haven't described how we've generated these rules, just stated that we can generate rules. Okay? So before we start talking about how to generate those rules, that's really going to be something we'll spend a lot of time in the next 2 sections working on. Let's do some examples just to kind of get used to the language of sequences and some of this notation. So let's say we want to write the first 6 terms of the sequence a sub n is equal to 2n plus 5. So the first 6 terms of the sequence are going to be a1, a2, a3, a4, a5, and a6. To generate the values for those terms, I'm going to be using this rule. And all I'm going to do is take my value for n and plug it into the space for n. So my first term is 7. And I'll just kind of continue doing this. And generate the values for each of these terms. Oops. Now, if you take a look at these term values, you should notice a pattern going on here. And we'll return to this idea of looking for a pattern in our term values a little bit more when we get to the next section. But I just want to point out now that this will be useful in helping us determine the rules for our sequence. So this is just, so writing the terms of a sequence is just like evaluating a function, right? You're just plugging in values of the domain into our rule to find our values in our range. Okay. Let's look at another example here. I guess I don't need to erase that. So let's ask the question, is 28 a term in the sequence a sub n is equal to 4n plus 6? Well, what we're going to do to figure this out is we're going to replace the 28 with the a sub n and then solve for n. So if I subtract 6 from both sides, I get 22. And if I divide both sides by 4, I get 5.5. Now, this has to then tell me something. So I have to remember that we're dealing with a sequence, right? So the n is a number in the domain. So I have to ask myself, is 5.5 in the domain? Well, if we go back and look at our original definition, the domain is a set of consecutive integers. Remember, the integers are positive or negative whole numbers, including 0. 5.5 is not a whole number. So what that tells me then is 28 is not a term of let's say a sub n equals 4n plus 6. Okay. What would it look like if it was? Well, let's ask this question. Is 26 a term in the sequence a sub n equals 4n plus 6? We'll kind of begin the same way. We'll subtract 6 from both sides and divide both sides by 4. And since 5 is an integer, we'll say yes, 26 is a term in a sub n equals 4n plus 6. So that's it. If you want to test if something's a term in the sequence, you're just going to plug it in and solve for n and check to see that you're getting a whole number. Okay with that idea? Okay. Up we're going to talk about series, which is the other half of a sequence. So next up is series. So now let's talk a little bit about a series. So when the terms of a sequence, instead of being listed in a, with commas separating them, are instead added together, the resulting expression is called a series. Just like a sequence, a series can be finite or infinite. So for example, a finite series might be 2 plus 4 plus 6 plus 8. An infinite series could be 2 plus 4 plus 6 plus 8, ... I remember the ellipse means that the pattern is going to continue, so the next one would be plus 10, plus 12, plus 14, and it just goes on like that forever. One way that we can use to more compactly write a finite or infinite series is with something called summation notation. So for example, the finite series 2 plus 4 plus 6 plus 8 can be represented with this set of symbols here. So this big E looking symbol is the Greek letter sigma. The I that's appearing here is called the index of summation. It's basically the variable that we're using inside of our summation. The lower limit of summation is what we start with here, and that's usually set to 1. The upper limit of summation is the number on top of the sigma symbol. And the 2i is the formula for the sequence that we're adding up. Now, the only thing that changes if we move from a finite series that has 1, 2, 3, 4 terms to an infinite series that has 1, 2, 3, 4, infinity terms, is that the upper limit for summation is changed to infinity. Whenever I see the ... I know the upper limit is going to be infinity. So let's look at a couple of examples to kind of get comfortable using our sigma notations. Okay. Okay, so in this example, we're going to write out the series for each sigma notation and then compute the sum. So let's say that our first sum is the sum from 1 to 5 of 2i plus 6. So what this is telling me is this is the sequence that I'm going to be adding up. I'm going to be starting with I equals 1 and ending when I equals 5. So the first term of my sequence, I'm going to plug 1 in for my formula of the sequence. To get the second term of my sequence, I'm going to plug 2 in. And because it's a series, instead of writing commas between these, we're going to write addition symbols. And we're just going to continue doing this until we've plugged in up to 5. Okay. So 2 times 1 plus 6 is 8. 2 times 2 plus 6 is 10. And we continue on. Okay. So that's my series. And now it asks for the sum. So that's 30, 40, 60 would be the sum. Now sometimes, if all I want is the sum, we can use our calculator to do this without having to write everything out. So let's look at that. Okay. So the place on my calculator that I'm going to be using is I'm going to press the math button here on the left side. And I'm going to scroll all the way down till I see the summation command. So I'm going to press enter there to select that. And now I'm going to type in what I see here. So the only change is that instead of using I as my variable, I'm going to use X. And just use my arrows to move to the different locations. And then press enter. And there's my sum. So I can also use my calculator to do something like this. Unfortunately, the calculator is not going to help me writing out the series because it's not going to give me each of these terms separately, but that's okay. The other thing that the calculator is not going to be able to handle is if this is infinity, right? So let's look at an example there. So let's say we want the sum, that's what the sigma symbol means, from 1, that's the first thing that we're going to add up, to infinity. Okay. Well, so I'm going to start by plugging, oops, that was supposed to be an I, right? This variable and this variable need to match. And then we plug 2 in for I, and then 3 in for I, and then 4 in for I. And that's probably good, because I know this is infinite, so it's going to have the dot, dot, dot at the end. So now I'll compute each of these. So 10 minus 2 is 8. 10 minus 4 is 6. 10 minus 8 is 2. 10 minus 16 is negative 6. And then we're going to keep going from here. But after this point, what do you notice is going to happen? 2 to the 5th, 6th, 7th, 8th, 9th. When I do 10 minus those numbers, we're going to be getting a negative value each time, right? So even though we have 16 here, we have a positive number for these first three, each one after that is going to be subtracting, and it's going to be subtracting a progressively larger and larger and larger value. So I'm going to write a minus sign with my 3 dots after it, because I know I'm subtracting from here on out. And if I keep subtracting over and over and over again an infinite number of times, I'm going to end up with a negative infinite number, right? It's going to get smaller and smaller and smaller and smaller until we get to negative infinity. Okay. And again, if you tried doing this on your calculator doesn't have an infinity button on it, so you couldn't type this into your calculator and expect to get a response from it. So that's about all we need to talk about here for this first section. It's just kind of getting used to using some of this notation and computing things out. Okay. So there'll be an assignment based on this, worksheet 1, and you should do that next. Okay,